Good morning, friends. I welcome you all for another session. In the previous session, we have seen how to find out the slope and deflection of a simply supported beam with a single point load at the center. Now, take another standard case, that is how to find slope and deflection of a same simply supported beam, but it is carrying UDL. Now, see, simply supported beam AB, okay, it is subjected to UDL over the entire span. So AB is a simply supported beam with a span, total span L. Okay, so since it is a two simple supports, reactions RA and reaction RB will be there, and it is subjected to UDL. As we know, since the load is symmetrical, it is a complete span, so the reaction will be total load divided by 2. So what is the total load now? Convert this into point load. Okay, what is point load now? So small w, that is intensity, into span. So W into L will be the point load. So this point load will be acting here center. So W, small w into L will be the point load, and what will be the reactions now? RA and RB. So that is WL by 2. So total load is WL divided by 2. So RA will be WL by 2 and RB will be WL by 2. So here we have found out, since the load is symmetric, okay, reaction RA and RB will be same, that is WL by 2. So this WL will be point load. So W into L will be the point load divided by 2. So reaction RA and RB will be same, that is WL by 2. Now let us calculate the bending moment now. Okay, so since it is a simply supported beam, so bending moment at A will be 0. Okay, bending moment at B will be 0. Okay, we will calculate bending moment at C now. So bending moment at A is 0, bending moment at B is 0. Now calculate the bending moment at this center point C. So either you can calculate from this considering portion AC or considering portion BC. So let us consider portion AC, only this part now. Okay, only this part. Now bending moment at C. So bending moment at C is equal to sign convention as usual. Okay, when you are calculating bending moment C, whether the beam will going to bend, that is okay. So if it is a sagging, it is positive. If it is a hogging, it is negative. Okay. Now bending moment at C now. So this is reference point. First take this reaction RA. Okay. So plus RA into L by 2. So this reaction, it is RA into, what is the distance between RA and C? It is L by 2. Half of this total span. So this is positive because when you apply this load, okay, when you apply this RA, this AC portion will going to bend like this. Okay, so when you push here from the bottom, this A goes top, so this beam will going to bend like this. Okay, then it is sagging. So sagging means positive. So plus RA into L by 2. So RA into L by 2 plus. Now see this UDL now. UDL acting between A and C. So first convert this UDL into point load. So what is point load now? So intensity is W. Okay, W into L by 2. Now we are considering only portion AC. So point load is W into L by 2. So W into L by 2. Okay, W into L by 2 will be acting center of this AC now. So W into L by 2, and distance between this point load and C is again half of this L by 2. This half of L by 2. So W into L by 2 into half of L by 2. This is minus. Now see, okay, when you apply this point load here now, so because of this point load, how this portion AC bends, it will going to bend like this. When you push from the top, it will going to bend like this. It will going to bend like this, means it is hogging. So it is minus W into L by 2 is point load into perpendicular distance between point load and C is half of L by 2. So this is bending moment at C. So if you calculate this, that is a substitute RA value. RA is plus WL by 2. So WL by 2 into L by 2 minus, see, it is WL square. This is L by 2. This is L by 2 and half. So WL square divided by 8. So if you take a LCM, Okay, so finally we're going to get bending moment at C is equal to WL square by 8. MC is equal to WL square by 8. Now with these ordinates, draw the bending moment diagram. Now first draw the beam ABC. So base of the beam ABC. Now mark these ordinates. So moment at A is 0 only, moment at B is 0, and moment at C, it is WL square by 8. See here, WL square by 8. Now in the previous case we have joined in a triangular form, but here that is not case. Now it is a UDL is acting here. So throughout span UDL is acting means here it is 0, here it is WL square by 8, this distance is WL square by 8, and here it is 0. So since it is a UDL, you have to draw parabolic curve. It is parabolic curve. So this is what the bending moment diagram. Moment at A 0, B 0, and moment at C is WL square by 8. And this portion will be L by 2, this portion will be L by 2. And above the baseline it is complete bending moment diagram is positive. So this is important step, how to find out the bending moment at A, B and C. So after finding out bending moment, draw the bending moment diagram. First reactions, then bending moment diagram. Next thing is, now we are going to calculate the slope. As you know, since the load is symmetrical, the slope at C will be 0. See this deflected shape. So because of this UDL, the beam will going to deflect like this. When the load comes on the beam will going to deflect like this. So if you draw tangent here, if you draw tangent touching at this point, so there is a theta A, slope will be there or rotation will be there at A. Similarly, if you draw tangent here, touching this point, so there is a theta B, that is rotation at B will be there, slope will be there. But if you draw tangent to touching this point, see this is a tangent for C at point C, if straight line here, so there is no rotation. So slope at center, that is slope at C will be 0, but slope at A is there, slope at B will be there. So now we are going to find slope at A, slope at B, that is rotation. See here, slope at support A, I am going to denote this as theta A. So if you want to find out slope, use the first theorem of Morse. Morse first theorem will be used. So using Morse theorem first, the slope at A. So slope at A is equal to what? So area of bending moment diagram between A and C. You have to consider area of bending moment diagram between A and C divided by EI. So why it is A and C only? Why it is between A and C? Now this is symmetrical. Now the slope at C will be 0. Slope at C will be 0 means we have to consider the bending moment diagram between A and C only. So what is the bending moment diagram between A and C? See this point, this portion, not complete. So only this portion will be considered, and see this is a parabolic. This is not a triangle. So this is parabolic area between A and C. Between A and C. So theta A is equal to area of bending moment diagram between A and C divided by EI. So write this equation 1. Now first find out this area of bending moment. What is the area of bending moment diagram between A and C? So area of bending moment diagram between A and C is nothing but area of parabola. See this is parabolic. Area of parabola ACD. So write this, mark this as ACD. So this portion, area of parabola shape ACD. So what is the area of parabolic? Area of triangle we know half base into height, but area of parabola is 2 by 3 base into height. Remember this. So if you get parabolic shape, the area will be 2 by 3 base into height. So 2 by 3, what is base? Only we are considering this much. So base will be L by 2. Base will be L by 2. Then height will be WL square by 8. Height we already calculated this. It is WL square by 8. So 2 by 3 L by 2 into WL square by 8. So 2 by 3 L by 2 into WL square by 8. So therefore area is equal to this 2 get cancels. So it is W L square and L is W L cube divided by, this is bottom 24. So area of bending moment diagram between A and C is W L cube divided by 24. So substitute this in equation 1. So therefore slope at A, theta A is equal to, okay, W area of bending moment diagram is WL cube by 24, okay, WL cube by 24 divided by EI. So this EI goes top, so WL cube divided by 24 EI. So slope at A is equal to, theta A is equal to WL cube divided by 24 EI. So similarly, so since the load is symmetrical, theta A and theta B are same. Similar slope at B is also same as that of theta A. So therefore slope at B, theta B is equal to same WL cube divided by 24 EI. Okay, so this is slope at A, slope at B, and slope at C is 0. Okay, now next find out the deflection at center. So as you know, again see here, so is there any deflection here? No. The beam will not going to deflect here. Since support is there, here support is there. So deflection will be 0 here. So deflection at A, that is YA is 0, YB is 0, but we have to find out what is YC. So after the load, the beam will going to deflect and it will come here. So this is the deflection YC. So YA is 0, YB is 0, but YC we have to find out deflection at C. So deflection at center, that is at point C, YC. Now YA is 0, YB is 0. Now if you want to find out deflection, we have to use the what? Morse second theorem. Okay, using Morse theorem for deflection, that is second theorem. So deflection at any point is equal to A into X bar. Okay, A into X bar divided by EI. So A is again area of bending moment diagram between 2 points. Okay, so where you want to calculate the deflection and another point into X bar. X bar is the, okay, center of gravity of that particular area. Then E is the Young's modulus of elasticity, I is the moment of inertia. Now see here, where A is area of bending moment diagram between A and C. So A is equal to, already we have calculated, this is area of bending moment diagram, we have calculated WL cube by 24. Okay, now X bar. What is X bar? Now see here. So this is X bar. Again we have to consider bending moment diagram between A and C, because at C, okay, slope is 0. At C slope is 0 and I want this deflection means, so you have to consider area of bending moment diagram between A and C. So only this portion. Now if you consider this again parabolic, okay, area we already calculated. And what is the centroid? This is not half. Centroid will be not half of this L by 2. Okay, so this is the centroid or center of gravity of this parabolic part. So the centroid will be from A, okay, from 0 point, it is 5 by 8 times of base. Okay, 5 by 8 times of this base. So base is L by 2. So it is 5 by 8 into L by 2. So this distance will be from A, this centroid will be 5 by 8 times of L by 2. So remember in the previous this thing, area we have find out 2 by 3 base into height, and centroid of this parabolic is 5 by 8 L by 2. That is from A. Okay, 5 by 8 L by 2. See, X bar is the distance of center of gravity of area from support A. So X bar will be 5 by 8 into base. So base is L by 2. So X bar is equal to 5 by 8 L by 2, that is 5 L by 16. So substitute this in equation 2, that is deflection equation here. Okay, so therefore Y is equal to deflection at C, YC is equal to A into X bar divided by EI. So area WL cube by 24, WL cube by 24 into X bar is 5L by 16 divided by EI. So it is 5, okay, WL raised to 4, okay, 5 WL raised to 4 divided by 24 into 16 is 384. So this is 5 WL cube by 5WL raised to 4 by 384. This goes top, that is EI. So 5WL raised to 4 divided by EI, that is deflection at point C. Okay, deflection at A is 0, B is 0, and deflection at C will be 5WL raised to 4 divided by 384 EI. So we have find out three quantities: slope at A0, that is slope at A, theta A, WL cube by 24 EI, and slope at B same, WL cube divided by 24 EI, and deflection at C, that is YC is equal to 5WL raised to 4 divided by 384 EI. So these are the standard quantities for simply supported beam subjected to complete UDL. Okay, so I hope you understood this. Okay, once again practice this. If any difficulties are there, so please contact me. Okay, so in the next session we'll coming up with another standard cases. Okay, thank you very much for attending this session.